So I couldn't resist a question that combines the work energy principle with the work we've been doing on power. So here goes. A car of mass 1,200 kilos pulls a trailer of mass 400 kilograms up a straight road inclined at an angle alpha to the horizontal, where sine alpha is 1/14. The car's engine works at a constant rate of 60 kilowatts. Non-gravitational resistances to motion are constant and of magnitude 1,000 newtons on the car and 200 newtons on the trailer. And at a given instant, the car is moving at 10 meters per second. So I would personally definitely do a diagram here so we can see what's going on. So we've got slope, angle alpha, and we've got a car. Sorry, it doesn't look very car-like today. And a trailer. And they're going up a straight road, and at a given instant the velocity is 10 meters per second. And the mass of the car is 1,200. Mass of the trailer, 400. So we've got 400 G, 1,200 G. We've got this driving force coming from the car. We've got normal contact forces, which I'll just call R, but NCF is fine. And then resistances to motion. So resistances on the trailer is 200 newtons, and these are modelled as being constant. And resistance on the car is 1,000 newtons. And the first thing we want to do is find the acceleration of the car at this instant. So if the car is working at a constant rate of 60 kilowatts, we can use power equals FV to find the driving force of the car. So the power is 60,000, and that's equal to the driving force times by the speed. And so dividing by 10, the driving force is equal to 6,000 newtons. And then to find the acceleration, we can use F equals ma. It's a good idea just to jot down what you're using as you go along. And so resolving forces, I've got 6,000 going up the slope, and then minus the resistances. I've got minus 1,000, minus 200, and then I need to consider the weight as well. So here, this component of the weight acting parallel to the slope is 400 G sine alpha. Because we want the opposite to alpha, and here, this little bit here, is 1,200 G sine alpha. So that is equal to the total mass, because they're travelling in the same direction. We could treat this as a whole, we don't have to split it across the tow bar. So that's equal to the total mass, which is 1,600 times by the acceleration. So we have got tension acting here. So we've got tension going that way on the car and that way on the trailer, but they're cancelling each other off when we do the equation of motion for the whole thing. So tidying that up a little bit. we've got 4,800 minus 1,600 G, and we know that sine alpha is 1/14 from up here, and that's equal to 1,600 A. And if you pop that into a calculator, A comes out as being 2.3 meters per second squared. So it's power equals Fe to find the driving force, and then F equals ma on the whole system. Right, second bit, we want to find the tension in the tow bar. And to find the tension in the tow bar, you could either work with the car and the forces acting on the car and use F equals ma, or you could just look at what's happening with the trailer, which involves less forces. So I kind of thought it made sense to use the trailer. So for the trailer, F equals ma. So we've got the tension going up the slope minus 200 resistance to motion minus 400 G sine alpha, which is the resistance to motion from gravitational forces. So that's resolving all the forces acting on the trailer. So we've got T minus 200 minus 400 G sine alpha. And that's equal to the mass of the trailer times by the acceleration, which is 2.3. And if you pop that into a calculator, you end up with the tension in the tow bar equaling 1,400 newtons. And then the last bit, the tow bar brakes when the car is moving at 12 meters per second. Find, using the work energy principle, the further distance that the trailer travels before coming instantaneously to rest. So we need to think about the change in kinetic energy. And the change in kinetic energy, whether it's positive or negative, will be a half m, so half times 400. And then it's the final velocity squared minus the initial velocity squared. And the sign of that will come out correctly. So that comes out as minus 28800 joules. So that's a change in kinetic energy, but it's a decrease. We know it's decreasing because it's going from 12 meters per second to 0. And then the potential energy is increasing as it's travelling uphill. So increase in potential energy is m g h, and we want the distance it travels before coming to rest, which we can call x. So that's the distance it travels before coming to rest. And the increase in potential energy would be this height here, and this angle here is alpha. So sine alpha is h over x, so h is equal to x sine alpha, but we know that sine alpha is 1/14. So multiplying all those together, you get 280x joules for the increase in potential energy. And then setting up the equation of motion, because the resistive force on the trailer is taking energy out the system, so minus 200x, so that's the work done is 200x, but we're going to subtract it because it's taking energy out of the system, and that's equal to minus 28 28,800 for the loss in kinetic energy, plus 280x, which is the gain in potential energy. So this is our change in mechanical energy, and that equals the work done by external forces. And from there, sorry, wrote that wrong. 28,800 is equal to 480x, and so x is equal to 60 meters. So if you go into a lesson plan, I've put a couple of questions for you to do on the next 2 pages. So there's a couple of questions with mark schemes which involve power, and just a little bit of recap on the work energy principle.